first job at a radio observatory, I had found the source which I was monitoring. And the sources, I had two sources, opposite sides of the galaxy. And one was doing this, and the other one, they looked like they were working together. They were getting brighter and weaker together. And I said to my boss, this is alien. It's gotta be, you know, because it's 10,000 light years apart. It takes 10,000 years for light to travel to the opposite sides of the galaxy. It's impossible for two signals to be in sync, to be correlated, like we're seeing here. And he thought I was nuts. Of course he did, and he was right. But if I would have had my brain on my head, which I didn't know then, I would have realized one of them was periodic. It was doing what the blue line was doing, or the red line is doing, and all that happened is my other source was not periodic, but it was just getting brighter at the same time the other one did. So this one was always doing this, and the other one was doing it occasionally. So for a period of 500 days, they looked like they were operating together. So if I would have had a brain on my head, and I hope you guys are better than me, you will have noticed, you would have detected periodic mazes, which is the biggest find in millimeters and in radio astronomy since probably they detected masers back in the 60s. And that was found by a woman named Sharmila Goodhart. She was a successor of one. She took over for the monitoring program after I left. And she noticed the objects were periodic. Good for her. It means she's a good astronomer. Okay, so, and that's the story. So that's the story of masers, and that's me. With Kitty. So for those of you who don't like leopards, don't get in that cage. So Kitty has come out to play. The black one liked to bite, So let's let that go. Anyways, what else you can do with a millimeter telescope is you can look at galaxies. And you can see here, you can see in the background, this is the Hubble telescope in the optical. You can see it in the background. And this is made by mapping it with a millimeter telescope. And this is another galaxy, so they're looking at the gas, the H1 gas. This is the CO gas, so carbon monoxide. And the optical is the blue. So you're looking at the blue dots are Hubble. And that's a galaxy, I don't know, it's probably 10 billion light years away. So you can do more than just star formation, but it's what I do, so I only talk about star formation. So that's the science of the telescope that we're talking about that can be done on Kilimanjaro. And I won't try to keep you much longer, except that I wanted to show you why these three groups want a telescope in Southern Africa, so they can do field eye, so they can make this map right here. This is the shadow of a black hole. This is what they expect to see if they get enough resolution, if the telescopes are far enough apart, and they have four of them. They have to have 4 telescopes. So they want one in Southern Africa, South America, North America, and Europe. And if they can get those 4, they expect to be able to make this image right here, and that is the shadow of a black hole. That's what a black hole, that's a simulated shadow of a black hole. And so from that, they expect to get themselves a Nobel Prize, and I get a piece of cake from the guys who won the Nobel Prize. Because they'll have a big party for all of us involved, and I'll get a piece of cake. So what the hell do I care if they win a Nobel Prize? I don't really care. But I do care about them building in a good site. And when you build a telescope, if you're going to spend $20, $30 million on a project, put it in the best site possible. Don't put it on at 2,300 meters in a site where they get high heat temperature because it's a hot wind that blows across. Hot winds carry moisture, right? Everybody knows hot air rises, correct? Yes. Hot air holds more moisture than cold air. So if you have a hot air current floating over your head, like here in Tanzania, we get a warm air current coming off the Indian Ocean, right? It's bringing moisture with it all the time. That's a no-no for astronomy, millimeter astronomy. You want a site that's got a cold air current. These guys want to build a telescope in Namibia where they've got a hot air current flowing right across the mountaintop. I mean, this is just silly. Why do I want to invest $20, $30 million into a spot that I know is not going to be a very good site? It'll be okay, but it won't be great. And it certainly is not going to be 4,000 plus meters. So these are the comparisons. So I just give you an idea. The Hafsburg is in Namibia. That's the blue. The red is Kilimanjaro at 4,600 meters. And what I'm looking at here, the tau, the value tau, is a measure of the transmission rate, the ability of the radio waves to get through the atmosphere. You want it to be less than 0.3. So anything less than 0.3 is good, which is down here. Anything above 0.3 will be crappy, will be terrible. You can still use it, but it'll be terrible. So you can see the Hafsburg during the winter months is as good as the Kilimanjaro site, but it's never better than the Kilimanjaro site. Okay? Now, to compare Kilimanjaro to the best site in the world, I compared it to Alma, and Alma is in black. Okay, it's the black lines, and the red lines is the Hafsburg. So you can imagine this spot down here, now we're at 5, all of this is blown up, and that's all the red. And the Kilimanjaro, the Alma site is better than Kilimanjaro. Okay? Not surprising, it's at 5,000 meters. And we're comparing it to the gold standard, remember? This is the gold standard. The black is the gold standard. When I first saw that, I actually stared at that image for Alma. I stared at it for 10 minutes because I couldn't believe how good it was. I mean, it really is very impressive. As an astronomer, this is like looking at funny magazines. This is what we do for a living. We stare at these silly graphs and stuff like that. But you can also see that the Kilimanjaro site is very good. It's actually very close. Look, here's the black up here, right? So it's not like the Kilimanjaro site's much worse. It's similar. And the thing to remember is that very likely these are 3-hour measurements. So the data is actually every 3 hours. And you're going to find there's a diurnal effect on Kilimanjaro. So hot air rises up the mountain. So in the early evening hours, you're going to find this very terrible observing. But by the late evening, by midnight, 1, 2 in the morning, through to about 9 in the morning, you're going to have very good observing conditions. So even in the middle of the worst part of the season on Kilimanjaro, you're going to get observing here that is worth doing. So you're going to get hours that you can actually use the telescope, always. That is not true in the Hafsburg. The Hafsburg, it's 1.52. So this sky is opaque. Above that line, the sky is opaque. You cannot see anything. So that telescope is going to lose 50% of its observing all the time. And it's only going to be decent in the winter months. So why do I want to spend to put a telescope someplace? So I beseech you guys, we need to put this thing in Tanzania on a very good site. And Kilimanjaro is the only site that's capable of doing that. Mount Kenya is another possibility. We looked at that. The problem with Mount Kenya is it's a mountain range. Kilimanjaro is a single mountain. And as a result of that single mountain, the weather will come in and it'll climb over the entire mountain range. And it'll dump its rain up the slopes of that mountain range. Whereas Kilimanjaro, the weather goes around it. It's not a wall, right? So the weather tends to go around Kilimanjaro. So you get some going over, but most of it goes around it. So Kilimanjaro is a much better site because it's a single mountain. It's identical to Mauna Kea in Hawaii. Okay, so that's what it is. So that gives you an idea of how good the sites are, and that's why I'm saying the Kilimanjaro site is so much better. And this is, again, I'm just showing you, this is the connectivity that they talk about. There's a telescope at the South Pole. Because of the extreme cold at the South Pole, it never gets above -40. It has very dry, very cold air, and it acts like a much higher altitude. Even though it's only at, I think it's at 2,000 meters above sea level, it actually acts like it's at 3,000 or 4,000 meters. So this is actually a very good site for astronomy as well, but that telescope is being turned off. So they need a site in Southern Africa here. So here, this was a students, they did a project where they proposed building a smaller set of antennas on Shira. They call it Shira. I forget what it stands for. And these are telescopes in Europe, and here's Alma, the best site in the world. That's the VLBI network they want to create.
Shira is on Kilimanjaro.
Yes, yeah, it's one of the other peaks, right?
No, it's an area.
It's an area, okay. And that's why they called it Shira. That's why I thought, okay. So that's why they want a site in Southern Africa. Whereas Namibia is right here. I've also gone to a site here in Lesotho called the Sani Pass. I almost died on the Sani Pass. Astronomy is not for sissies. It's very dangerous. No, seriously, I'm not kidding. I took my cell phone out. I was wearing it was very windy, extremely windy. You're at 3,000 plus meters. And I was wearing a loose-fitting, I hate wearing coats. I was wearing a loose-fitting jacket, and the wind caught me like a sail, and it shot me towards the edge. And I almost got blown off the cliff. And I had to hit the ground, and I got pushed along the ground on my backside, but I was okay. Then I walked the heck out of it. I got out of it. But it almost blew me off the mountain, all to take a photograph. So sometimes, astronomy can kill you. And I don't think Kilimanjaro will be any different. If we were trying to go to Mwenzi Peak, they're telling me it's a very dangerous climb. So that would be an example of a very dangerous climb as well. And so to do this site selection is actually quite interesting and quite exciting and actually quite dangerous sometimes. I know guys went up into the Himalayas as well. It's dangerous. You could freeze to death. You could get blown off a mountain like I almost did. So we're going to have to fatten up when we go up there. You're just too skinny. I mean, you're going to be like an airplane flying off that mountain. So anyways, so that's why we want to do stuff like that. And here's the site, as I said, here's the site again at 5150. That's where we hope to go. And if you zoom in on that on Google Earth, you get a really good feel about how rough the terrain is. There's actually a very nice flat spot up there, by the way. It's about 300 meters by 400 meters area, right on the top at about 5,100 meters. That's actually really good for building a telescope on. But to get to that spot is not easy. It's going to be it would be good. And I don't know if we would be able to, because you'd have to build a road to get stuff up there, and then it's going to look terrible. Can you imagine me standing on Uhuru Peak looking down at Mwenzi? You got this stupid road that zigzags all the way up the side of the hill. It will look terrible. So I don't know if we would want to do that, because it would destroy the atmosphere for the tourist trade that's there, right? And the key here is we would need a road, and that's what I've said here. So to build roads, you got to get equipment from the base up to the top. You need a road. And the equipment is quite big. Here's the equipment they used to move that telescope. And this was the telescope I said that was promised for us, for Kilimanjaro. Now look at what it took to get it up there. This is 5,000 meters. So you can imagine this is a nice plowed road. The road going up Kilimanjaro right now does not look like that. No, as I said, I've been up there. It's not, no.